Hi everyone, and welcome to session 1A of Thursday program of QIP. It is my pleasure to introduce now Giacomo De Palma, who is going to talk about the quantum Wasserstein distance of order 1. So please, Giacomo.
Good morning to everybody. So first of all, I would like to thank the organizer for this wonderful organization of the conference in this difficult situation and for giving me the opportunity to present this recent work. So this is a collaboration with Milad from University of New Mexico, Dario from the University of Pisa, and Seth from MIT. And it concerns a quantum generalization of the Wasserstein distance, or more informally, a quantum version of the Hamming distance. So let me start with the motivations for this work. Most of you will probably know that the Hamming distance is ubiquitous in several fields like classical probability, information theory, machine learning. And in the quantum setting, there is still no real counterpart of the Hamming distance. For example, we would expect one for states of n qubits or qudits. And what the Hamming distance captures for bit strings that is not captured by the usual distances on qudits is that flipping a single bit in a string is a small change with respect to the Hamming distance, because this is a change, change is only one bit. So, but if you flip, for example, a qubit in a set of n qubits, in general, you will generate a state that's orthogonal to the initial state, and this state will have a maximum distance from the initial state with respect to all these standard distances, such as trace distance, fidelity, or relative entropy. Or like all these distances have this property that are unitarily invariant. So they are invariant if you apply a unitary to both states. And in this case, any couple of pure orthogonal states have maximum distance. So the idea of this work is to find a distance between quantum states of qudits that possibly recovers the Hamming distance for the states of the canonical basis. And more generally, that has the property that any quantum operation performed on a single qubit induces only a small change. And one desirable consequence of this property is that we wish global quantities like global energy or global entropy of the state to have nice continuity properties with respect to the distance. So in the classical setting, we do not only have the Hamming distance between the bit strings, but we have a distance with this property between the probability distributions on bit strings. And this distance comes from the theory of optimal mass transport and has the name of Wasserstein distance. So the idea of optimal mass transport is that we consider probability distributions on a metric space, that in this case is set of bit strings with the Hamming distance. And we interpret these distributions as distributions of a unit amount of mass. And then we say that moving a unit amount of mass from the point X to the point Y of the metric space has a cost that's equal to the distance between X and Y. And then it is natural to associate to any two probability or mass distributions P and Q a distance which is equal to the minimum cost that is necessary to pay to transport P on Q. And this distance takes the name of Wasserstein distance, or Earth-Movers distance, or Monge-Kantorovich distance. So one key property of this distance that will be relevant for the quantum case is that it is actually induced by a norm, and then it actually depends only on the difference between P and Q. And this field of optimal mass transport has been an extremely fruitful field in mathematical analysis with countless applications in several fields like geometric analysis, probability, information theory, and also machine learning. And of course, as I anticipated before, we will focus on the case where the metric space is the set of strings of n bits or of n symbols taken from some finite alphabets. And we will consider the Hamming distance on this metric space. So let me go to the quantum case. And I remember that the main desired property of this distance that we want to define is the robustness with respect to local operations. So we define two quantum states of n qudits to be neighboring if they coincide after a suitable qudit is discarded. And then we want the state to be close with respect to this new distance. And then we require that any couple of neighboring states has distance at most 1. And then, as in the classical case, we require that this distance will be induced by some norm on the set of the density matrices. And we will take the maximum norm with this property. So the maximum norm that assigns distance at most 1 to any couple of neighboring states. So how do we achieve this? Clearly, all this, so this is a difference. So these rho I and sigma I are states that differ only in qubit I, in the sense that coincide after qubit I is discarded. So they must have distance at most 1. So their difference must have norm at most 1. And since any norm has to satisfy the triangle inequality, also the convex hull of these differences must lie in the unit ball of the norm. And then the maximum norm will be the norm induced by the minimum unit ball, and the minimum unit ball is exactly the convex hull of all these differences between neighboring states. And then, as I anticipated, this gives rise to this Wasserstein norm that is the maximum norm that assigns distance at most 1 to each couple of neighboring states. So now we have this distance. Let's look at its properties. So one of the requirements was, decided requirements was to recover the classical case. And it's actually possible to prove that this distance recovers the classical Wasserstein distance for the states that are diagonal in the canonical basis. And in particular, it recovers the Hamming distance for the states of the canonical basis. Then, once you have a distance, you may want to look at the symmetry satisfied by the distance. And this distance is invariant with respect to unitary operations acting on a single qudit, and with respect to permutations of the qudit. And this follows directly from the definition that has the symmetries. Then another property of this distance is that it is, in general, it's not contractive with respect to any quantum channel, but that was expected and desirable. But if you apply a quantum channel to a single qudit, then this distance is contractive. Another fundamental property is the behavior with respect to the tensor product. So if we take a tensor product of two couples of states, as you see here, the distance between the tensor products is equal to the sum of the distances on the subsystem. So this distance is additive with respect to tensor product. And this is in sharp contrast with respect to, for example, trace distance. So also we would like to know how this distance compares with respect to the trace distance. And it is actually possible to show that this distance lies between the trace distance and n times the trace distance. And in particular, it lies always between 0 and n, where n is, of course, the number of qudits. Then I mentioned robustness with respect to local operations. And it is possible to prove that if we apply to a given quantum state some quantum channel that acts on at most k qudits, then this channel will displace the initial state by at most 2k, so twice the number of qudits. Okay, so as you probably know, one of the main properties of the trace distance is that it is contractive with respect to the action of quantum channels. So if we apply a quantum channel to two states, rho and sigma, this channel will decrease the trace distance. And a fundamental quantity that quantifies this contractiveness is the contraction coefficient of a channel that tells you the minimum amount of contraction that the channel is guaranteed to apply. So this is the maximum distance between the outputs, two outputs of the channel, divided by the distance between the inputs of the channel. And one property of this contraction coefficient is that if we consider the tensor powers of a given channel, so we consider many qudits, so the channel acts on a single qudit, we consider n qudits and we apply the same channel to each qudit, this contraction coefficient becomes trivial in the limit of n going to infinity, because assuming that the channel is not trivial and that there will exist two states, rho and sigma, that produce different outputs, then if we take n copies of phi of rho and n copies of phi of sigma, if n is large enough, they become almost orthogonal and perfectly distinguishable, and their trace distance will tend to their maximum value. So in the limit n going to infinity, the contraction coefficient of the nth tensor power of a given single qubit channel always tends to 1. While now we are looking at the properties of our newly defined Wasserstein distance, and we can look at the same quantity. So we can define also here a contraction coefficient defined as the maximum of distance between the outputs of the channel divided by distance between the inputs. And then we can ask whether the same property will hold or we get something interesting, and we actually get something interesting. So first case is when the channel is not necessarily a tensor product channel, but is induced by some quantum circuit. And here the relevant quantity is the light cone of the qudits. So here we have a qudit in the inputs, and here are the qudits in the output that these qudits can influence. And then it is possible to show that the contraction coefficient of the Wasserstein distance is at most twice the size of the largest output light cone of some input qudit. Then, coming back to this tensor power channel, in general, we can prove this property. So let omega be some fixed point of the single qubit channel phi, and let this E be the erasure channel that replaces the input state with omega. And then we can find this single letter upper bound to the contraction coefficient of phi tensor n, which is equal to the diamond norm, the diamond distance between phi and this erasure channel. And two applications of this property are the amplitude damping channel with decay probability 1 minus p, where this contraction coefficient is upper bounded by this quantity that does not depend on n, and the depolarizing channel that replaces the input state with some given state with probability 1 minus p. And also here we can compute exactly the contraction coefficient that is equal to p for any n. Now, I mentioned before that one of the desirable properties is the a nice continuity of the von Neumann entropy with respect to this distance. And actually, this property can be useful because for the standard distances like trace distance, of course, there are continuity bounds of the entropy with respect to the trace distance or the fidelity, but all these continuity bounds become void for orthogonal states because orthogonal states have maximum distance. And we know that flipping one single bit is not able to change the entropy by much, but still flipping a bit can turn a state into an orthogonal state. And then one would like some continuity bound of the entropy that applies also to this case. And we have been able to prove this continuity bound here for our distance for the von Neumann entropy. So here we have so this is the entropy difference. On the right hand side, we have this function g that is upper bounded by a logarithm, and then it's not much important. The fundamental part of the bound is this last term that tells you roughly that the entropy difference is upper bounded by the W distance times the logarithm of the number of qubits. And this tells you that if the W distance is small o of n divided by log n, then the entropy difference between two states will be small o of n. And actually, there is a similar continuity bound for the Shannon entropy in the classical case, and this log n there is not present. We conjecture that this log n is an artifact of our proof, but we have not found a way to get rid of it yet. Then we have also defined a quantum version of the Lipschitz constant that allows to formulate a dual definition of the quantum Wasserstein distance. And this quantum Lipschitz constant of some quantum observable is defined in this way. So for each qudit, we consider the operator norm of our observable H minus some observable that does not act on the qudit I. And then we minimize over all these subtracted terms that do not act on qudit I. And we maximize over the qubits. It is possible to show that this definition, in the case of operators that are diagonal in the canonical basis, recovers the classical Lipschitz constant of functions, that is the difference in the value of the function divided by the distance between the two inputs. And the fundamental property of this Lipschitz constant is that it provides a dual formulation of the Wasserstein distance as the maximum difference in the expectation value on the two states of some operator that has Lipschitz constant at most 1. And this allows us to formulate the computation of this Wasserstein distance as a semi-definite program, and this Lipschitz constant provides the dual of the program. Another fundamental distance in information theory is the relative entropy. And regarding the trace distance, there is a fundamental relation between trace distance and relative entropy, that is the Pinker's inequality, this one here. So we want to look at what we can say for the W distance, and we have an answer in the case of tensor product states. And we have been able to prove that the W distance between a generic state and a completely product state is upper bounded by the square root of n over 2 times the relative entropy. This inequality holds also in the classical case and is known as Marton's transportation inequality. And then we call this inequality quantum Marton's transportation inequality. So one of the fundamental property of the Lipschitz constant of functions is that in very high dimension, functions with a low Lipschitz constant are essentially constant. And then we want to check whether the same property holds for quantum observables with respect to our Lipschitz constant. And the answer is positive. So we have been able to prove first this upper bound on the partition function of a generic observable in terms of the Lipschitz constant. So here we consider some traceless observable, and the partition function is the logarithm of the partition function is upper bounded by the square of the Lipschitz constant. And actually, a fundamental consequence of this upper bound of the partition function is a concentration inequality that tells you that most of the eigenvalues of H actually lie in a small interval whose size is square root times square root of the number of qubits times the Lipschitz constant of the observable. And more precisely, this is the exact expression for this concentration inequality. Okay, let me come to the conclusions. So we have defined a new generalization of the Wasserstein distance to the quantum states of n-qudits, and this can have as the Wasserstein distance and the Hamming distance as countless applications in the classical setting. This distance has all the right properties to have a lot of applications in quantum information. So one application is employing it as a robustness measure for quantum machine learning. So to measure the size of a perturbation in the input of some algorithm for quantum machine learning. A second application is in the context of quantum generative adversarial networks. So this distance can be employed as a cost function for these networks that have the goal of learning a quantum state. And you can read more about this in this recent paper that we put on the archive a few weeks ago. Then this distance can provide the right quality factor for quantum brain distortion theory that concerns the transmission of a quantum state where some error from imperfection in the recovery is allowed. Then I talked about the contraction coefficient, and this distance can lead to better explorations of the mixing time of quantum Markov semigroups. Then I said that this distance is robust with respect to the application of a shallow quantum circuit, and then can be employed to explore the computational capabilities of these shallow circuits. And finally, this distance can be extended to the case when the number of qubits or qudits is infinite to explore quantum spin systems on infinite lattices. So that's all. Thanks for the attention.
Great. Thank you very much, Giacomo, for the nice talk. It was really interesting. It seems that there are a few questions on Slack, so I will start asking them to you. For example, Daniel Gottesman is asking, is there any connection between quantum error correction and the quantum Wasserstein distance? Like, for example, is the distance of a QECZ equal to the max Wasserstein distance between code words?
That's something that we are currently exploring. So definitely, if we know that we can convert, like what we are exploring is what's the Wasserstein distance between code words in some quantum error correcting code. And of course, if we know that we can convert a code word to another code word by applying a given number like k single q, like k Pauli operators, then we know that the distance between these two code words is at most k. One conjecture is that the distance between two orthogonal code words is exactly equal to the minimum number of Paulis that we need to apply to convert one code word to the other. But this is still under exploration. It's something we'll be happy to discuss better.
I see. Well, thanks. We have another question, for example, from Richard Quinn, who's asking, is there an interesting relation between the quantum Wasserstein distance of order 1 and the complexity of a quantum state? Like, I don't know, suppose I know that the Wasserstein distance of two pure states. Does this provide a lower bound on the minimal circuit size required to transform one state into the other?
That's also something that we are exploring. One thing is that by construction, this distance is upper bounded by the number of qubits, while we know for sure that there are states that require exponential size circuits to be built. So this can't directly work in the naive way, but it may be that there is some relation between these two things, like complexity and the distance.
I see. Great. I mean, we still have some time for another question, if it appears. If not, in the meantime, I would like to ask you, because I'm quite interested on quantum Markov semigroups. So could you please say a little bit more about this perspective of applying your results to the mixing time of such semigroups?
Okay, so as I was saying before, here the point is that this distance has a non-trivial contraction coefficient when you consider a given one-qubit channel applied to all the qubits in an n-qubit system. And usually the quantities that people look at are the contraction coefficient of the trace distance that becomes trivial in the limit of infinitely many qubits, or the contraction coefficient of the relative entropy. But this coefficient becomes like in the case where the fixed point of the semigroup is a pure state, that for example, you have it for the attenuator channels, then you can't, like, it doesn't make sense to define the relative entropy with respect to the fixed point, and then people have to use other methods. So the idea is that this distance can provide insights on the convergence of these semigroups without suffering from issues when the fixed point is not full rank.
Great, makes sense. Okay, so thank you so much for answering these questions and for the very nice talk.